Okay, so I think we can start. No? Yeah. Okay, so good morning and very warm welcome to all. The slides of this talk is also available on our web page of CATGT. You can access from there. So we have also put the slides of this talk in this chat box. You can also access from there. And today we have Dr. Arindam Banerjee from Ramakrishna Mission Vivekananda Educational and Research Institute, Kolkata. He will be speaking on age ideals and their resolutions. Arindam, over to you. You can start.
Okay, thanks a lot to the organizers for inviting me for this talk. Um, I am actually an odd person out in this conference because I am actually going to talk mostly about algebra, which I understand is not part of the panorama that this conference covers. The reason I am speaking in this conference will be clear if I give you a little background of what I'm going to talk about today and why I'm giving this talk in this conference. So, age ideals are essentially ideals in polynomial ring. I mean, I'm assuming people are familiar with at least this much. You take a polynomial ring on certain variables over a field, and age ideals are ideals in that polynomial ring, which comes with certain finite simple graphs associated to that. Now, why study such things? So until recently, what happened was in algebra and algebraic geometry, lots of abstract theorems were proved. However, concrete theorems like characterize, for example, all rings of dimension 2 or whatever. Tackling such questions were extremely hard. One could build theory and nice structures like various homologies and so on, but actually proving something as concrete as this was very hard. So that's where the combinatorial structures came. What people started studying was algebraic varieties, or in particular ideals in rings, which comes with certain combinatorial structures associated to that. And in terms of that combinatorial structure, one wanted to study that algebraic object. So edge ideals became popular. This became extremely popular in middle to late 90s, and really lots of work started happening in first decade of 2000s. And so what happened was this was my edge ideals and their resolutions. I'll explain in a moment what I mean by that. That was the topic of my PhD thesis. And after my PhD, during my postdoc, I was visiting CMI, and my teacher, who was in ISI when I was a student, B.V. Rao, Professor B.V. Rao, he asked me a question like, what happens if you're studying these things? What happens if you study them for random graphs? And until then, I really never thought anything in that direction. So then at some point I was visiting ISI Bangalore, and I asked Yogesh, actually, these are the results we have for usual graphs. Can one study the same things for the random graphs? And we started interacting, and we got some interesting results. So I'm supposed to talk about the algebraic preliminary and the algebraic side of the picture today, and Yogesh will talk about more of the random side tomorrow. So that's the background of this talk and me being here. So let me now start with the content. Let S be a polynomial ring, and let G be a finite simple graph with vertices x1, x2, xn. So now the variables in the polynomial ring have two meanings. They are the indeterminants of a polynomial ring, and as well as their vertices of a graph. Well, what I mean by finite simple, it simply means undirected graph with no loop, no multiple edges. That is, there is no direction for any edge, and between two edges there can be at most one edge, no multiple edge, and no vertex can be connected to itself. The edge ideal of G is the following ideal. Just take the square free quadratics that denotes the edges. Take the ideal generated by that. For example, if G is this graph, the triangle, the edge ideal is just the edges x1, x2, x2, x3, x3, x1. Any questions so far about the edge ideal? Is there anything that is not clear about the definition of edge ideal? Because I'll not come back to the definition after this. It's a square-free quadratic monomial ideal in the polynomial ring. And in fact, one can very easily see that for any edge ideal, there is a square-free quadratic monomial ideal, namely the ideal. Any finite simple graph, there is this square-free quadratic monomial ideal, as well as for every square-free quadratic monomial ideal, there is a finite simple graph. This is a 1-1 correspondence. These dictionary buildings are extremely important in mathematics, and this is what we are essentially heading towards. So let me define one concept which is extremely important for me, namely the concept of induced subgraph. A subgraph G prime of a finite simple graph. By the way, all graphs in today's talk will assume until the very last slide is going to be finite simple graph, finite simple undirected graph. A subgraph G prime of G is called induced if UV is an edge of G prime whenever UV are vertices of G prime and UV is an edge of G. This is if and only if. That is, you take bunch of vertices and keep all the edges intact. Just to explain with an example. Suppose G is this graph. The induced subgraph on W1, W2, W3 is this triangle. So no, there is no edges between W1, W2, W3 that is missing. A non-induced subgraph on W3, W4, W5 will be this. Look, the W3, W4, W5 makes a triangle in the original graph. In this graph, the edge W4, W5 is missing. Remember, the induced subgraph means that if you have certain two vertices and there is an edge between them in the original graph, that has to be preserved. Presence or absence of various induced subgraphs have algebraic significance. And this is where this is what makes induced subgraphs so important for our talk. So now let me define what I mean by algebra for today's talk. I mean, what really the algebraic concepts that will be relevant. Let K be this S be a polynomial ring. By the way, this field, I mean, I started with arbitrary field for today's talk and also for Yogesh's talk. This field will not be that much important. Whatever the results we are talking about, that works for every field. In this area, the field becomes important for certain results. Field becomes important in a sense the characteristic of the field, that is minimum number minimum number of time minimum number n such that 1 plus 1 plus 1 n times equal to 0. That number becomes important, but not for today's talk or Yogesh's talk. So let I be a monomial ideal in this polynomial ring. There exists an exact sequence called homogeneous minimal free resolution of I. What do I mean by that? Here is I. There is this map. So there are these Fs, which are free modules, free S modules. That means S direct sum S, direct sum S certain amount of times, finitely many times. And a map from F0 to I. So first of all, I to 0, there is this usual trivial homomorphism. Everything goes to 0. There is this from F0 to I, there is a homomorphism. F1 to F0, there is a homomorphism. Up to certain point, finite and 0. These Fis are free modules over S. That is direct sum of its free module is like vector space. I mean, these are basically direct sum. There is a basis and it's just a direct sum of the base free. What I mean by homogeneous, I'll not explain too much because it won't be important. I'll just briefly explain. There's a condition we need. The kernel of each of these DIs will be same as image of the next one. That's the exactness condition. And the rank of this Fi has to be minimum number of generator of each of these kernels. So what we do is the following. Take generators of I. Suppose I has k many generators, take minimum generating set. Take S power k and send ith basis element to the ith generator. That gives you a surjection. That surjection will give you a kernel. Since we are in polynomial ring, that kernel will be finitely generated. Take a minimum generating set of the kernel. Take a free module of that many, so they take that many copies of S, that is free module of that rank. Again, send ith basis element to the ith generator of that kernel. That gives a surjection, and keep going. This process ends. That's a deep theorem. That's called Hilbert-CZG theorem. This process ends because we are in a polynomial ring. That gives you a way to study I in terms of free modules. So this is called minimal homogeneous minimal free resolution. I'm coming to the homogeneous word, but the resolution, the word, essentially comes from repeated solution. There is a fantastic book which unfortunately is a sort of second course on commutative algebra by David Eisenbud. It's called Geometry of Czgs, which is devoted to study of these resolutions. These are standard ways to study ideals and their relation between various generators. Being homogeneous is a technical condition, which means elements of certain degree goes to elements of same degree. Now, if you have polynomial, what does degree mean? Well, if you're in a polynomial ring, the scalars have degree 0. The linears like x plus y have degree 1. For example, ax plus by, where a and b are scalars, also have degree 1. Quadratics have degree 2. For example, x square has degree 2, x square plus xy has degree 2, and so on. However, elements like x square plus y, this doesn't have a degree. These are not homogeneous elements. So basically, every polynomial, for a polynomial is called homogeneous polynomial if each of the monomials appearing there have same degree. Now, what do we mean by homogeneous for direct sum of various, an element in the direct sum? I'll leave that, but there is a, let's say it's similar. It's a generalization of this notion that if you have a map from a polynomial ring to polynomial ring, that will be homogeneous. If linear polynomials go to linear polynomials, quadratics go to quadratic, and so on. And there is a generalization of that concept in the free modules. So that's a technical condition. We can also make sure that there exists a minimal free resolution which satisfies that homogeneity condition, and hence we have a homogeneous minimal free resolution. But what is most important in this picture is that these DIs, D1 onward, these DIs are maps between free modules. Now, free modules have bases. So each of these maps have metrics present.
Arindam, there is a question in chat box.
Oh, can somebody?
Yeah, each P unique.
Huh?
Each P unique. This is the question. I mean, you
What?
can ask. Each P unique.
Oh no. Yes. P is unique. I mean, in fact, homogeneous minimal free resolution is unique. I mean, the uniqueness I don't need for today's talk, but yes, it is unique. If you put the minimality condition, it is unique. And this minimality comes from this condition that rank Fi is equal to minimum number of generators of kernel Di. If you enforce that, then this becomes unique. Yes, P is unique. And in fact, P is an extremely important invariant. It's called the projective dimension of I. But what is important, for most important fact is that each Di, I greater than equal to 1, is that they are maps between free modules, and hence they have matrix representation. And of course, which ring the entries of the matrix come? They come from S. Now, if these matrices have very simple form, then I will be, let's say one can assume that I has nice property. So that's what I just observed, that each Di is a map between two free module and hence has entry from S. I is said to have a linear minimal free resolution if for all I greater than equal to 1, entries of Di are either 0 or linear. That is, entries of Di's come from the polynomial ring. So they are either 0 or linear, that is of the form 2x1 plus 3x2 plus 4x3 and so on. They don't have any quadratic term appearing in them. Now, this linear minimal free resolution may appear somewhat technical condition. It is not very technical, it's very natural in this context, because at least let's concentrate for a moment to the square free monomial case. Instead of monomial, just only take the square free monomial case. For every square free monomial ideal, there is another square free monomial ideal which is called its Alexander dual. Now, in algebraic geometry, there is a very interesting or important concept called Cohen-Macaulay. Cohen-Macaulay essentially means two different important notions of size, namely the Krull dimension and depth. They coincide, and in fact, famous algebraist Hochster once made this statement that life becomes worth living in Cohen-Macaulay rings. So people are always interested to get things which are, or classes of things which are Cohen-Macaulay. If I has linear minimal free resolution, then its Alexander dual is Cohen-Macaulay. And this is an if and only if condition. The Alexander dual is Cohen-Macaulay if and only if I has linear minimal free resolution. So linear minimal free resolution, apart from being, this resolution being really neat that only linear or zero entries can appear, it also has this deep geometric significance underlying it. Also, if all entries of the first map, not the zeroth map, the first map are linear, then I is said to have linear presentation. That is, the first map is linear, may not be the other ones. And linear presentation doesn't imply linear resolution for sure. Of course, linear resolution implies linear presentation. It's far away from that. So how much time I already? So let me give you an example to explain this resolution. Take this ideal x1, x2, x2, x3, x3, x4, x4, x5, x5, x1. I mean, I didn't draw the picture, but one can right away see that this is basically edge ideal of a pentagon, like an induced pentagon, a 5-cycle. Its resolution looks like this. It has length 2. It stops at p equal to 2 here. I'm not talking about D0 because this is sort of obvious map. It's a surjection. D1 looks like this, and D2 looks like this. F0 is just EIth basis go to I. And more importantly, F0 is, by the way, this D0 is not a map between two free modules. I is as far from free as it goes. So D0 doesn't have a matrix representation. So it doesn't make much sense to talk about matrix of D0. I mean, we know what D0 is, but there's no question of having a matrix. D1 has linear entries and zeros. So by the way, if I is monomial, it's not very hard to prove that each of these DIs will have, the matrices will have monomial entries. It's not very hard to prove, but it's a little technical, and again, unrelated to today's talk somewhat, so I'm just skipping that. So this is an example, by the way, where linear presentation doesn't imply linear resolution. It fails to be linear, have linear resolution because it breaks down there. So each module Fi has this form. Okay, this is a somewhat weird thing, but I hope everybody understands this direct sum, at least here, recognizes this direct sum. It's direct sum of these strange looking objects. What are these strange looking objects? S minus J is the module S with a different grading or different degree. S minus J of I is S of I minus J, and beta ij is the number of copies of S minus J in Fi. This invariant beta ij called ij Betti number of this ideal. I know that there are topologies, so I should have written that this is called graded Betti numbers, because in topology there is this general Betti number. These are called graded Betti number. That was a mistake on my part. I mean, I forgot that in the algebraic world, that when we talk about Betti number, this is what we mean. So let me explain with an example. Let S be kx1, x2. If you take minus 2, it's a free module kx1, x2. Here, the elements of K, the scalars, have degree 2. Now, K x1, x2 is your S minus 2. S minus 2 of 2 is what? S 2 minus 2 is 0. So the zeroth degree 0 elements in S are just the scalars. So the degree 0 element here are the elements from the field. S minus 2, 3. What are the degree 3th element? Well, this is S3 minus 2, which is just S1. So the linear polynomial. So the linears have degree 3. Similarly, the quadratics have degree 4 and so on. So this is called shift. Once you get used to it, it's not really hard. So S minus J is just S where you're calling the scalars have degree J, linears have degree J plus 1, quadratics have degree J plus 2, and so on. Why you have to do this? See, you want the linear minimal free resolution to be homogeneous. We said this homogeneity property at the beginning. Now, obviously you will not, if when you are sending basis element is 1 0 0 0 0, right? And 1 0 0 0, or if you just have one, suppose you have only one generator, suppose just you have a principal ideal I, when you are so let's say you have just one generator like x square, and you want to surject from Sx to ideal generated by x square, you will send 1 to x square. Now 1 going to x square is not degree preserving map. The way you make it degree preserving, you just give 1 degree 2. Why you are doing this? This is, I agree that this looks artificial and technical, but the point is how much, what you are essentially doing here, you're developing a mechanism to keep track of the degrees of the generators of the kernel. That's all. What you really want to do, you want to list what is the degree of the kernels. Now you may ask, just why not just keep track of the minimal generators of the kernel? There are benefits of this introduction of this terminology, and because using these Betti numbers, in a second we'll see, we'll sort of define an invariant called Castelnuovo-Mumford regularity, or just regularity, which keep track of an ideal being linear resolution or how far it is from linear resolution. So, and these Betti numbers also preserve many important geometric properties. So that's why we define and introduce these somewhat technical notions. Well, for today's talk, if you haven't followed what I'm saying or not, I have some doubts, I will only define Betti numbers to, we use a Betti numbers to define regularity, and we wouldn't get too much into that. So Castelnuovo-Mumford regularity of I is defined to be max of J minus I. By the way, this J minus I essentially keeps track of how big is the degrees of the generators of the kernel. So this max over J minus I, beta ij non-zero, is called the degrees of the, it's called the regularity. But what is important is the following. Linear minimal free resolution is the case of minimum possible regularity. If an I is an ideal generated in degree D, a fixed degree D, that is I is an ideal where each generator has same degree D, then it has linear minimal free resolution if and only if regularity is D. What does it say about edge ideals? Edge ideals are ideals generated in degree 2. This says edge ideals have linear minimal free resolution if and only if the regularity is 2. This gives us a direct numerical invariant to keep track of linear resolution. This is only one of the utilities of these Betti numbers. There are other interesting application of Betti numbers. By the way, there is this new theory called Boyd-Schoderberg theory, which essentially tries to write down any arbitrary module and take the Betti numbers and tries to find whether they can be written as or somewhat direct sum of whatever the direct sum means in this context, Betti numbers of simpler modules. And it turns out that it can be done using the pure submodules and so on, pure modules. And that's a different direction. But these are extremely important. So if you take this ideal, we saw its resolution. One can check the regularity is 3. How? So this is not a linear resolution. How? The resolution actually, we saw that it stops at third place. So this actually looks like this. D1 is this and D2 is this. So what does it say? Here at 0, the only Betti numbers that are non-vanishing are beta 0, 2. So 2 minus 0, 2. At 1, the only non-vanishing Betti numbers are beta 1, 3. So 3 minus 1, 2. At 2, the non-vanishing Betti numbers are beta 2, 5. So 5 minus 2, 3. So the max is 3. Hence, the regularity is 3. One can compute these resolutions using some computer algebra system like Macaulay or Singular. It's just input the ideal, they compute the resolution. So now the combinatorics. Why we bring combinatorics in the picture? In general, characterizing ideals, say if somebody asks you, can you characterize all ideals, let's say in all degree D ideals in a polynomial ring which has linear resolution, that just goes out of the window. For square free monomial ideal, there are some really complicated characterization using shellability and Alexander duality, because you go to Alexander duality and then you characterize a Cohen-Macaulay, but that in many ways essentially saying that, okay, it's just saying max of beta I minus j, beta ij non-zero is 2. That's not very concrete. However, edge ideal is one of the very rare case where actually minimal free resolution can be characterized completely. How? This is a theorem by Froberg. This came in 1990, that for any graph G, Ig has linear minimal free resolution if and only if the complement graph, I'm assuming it's okay. I mean, the complement graph is essentially you just take the same vertices and non-edges becomes edges and edges become non-edges. Complement graph has no induced cycles other than triangles. That is, if you have a 4 cycle, it must have an edge. It cannot be an induced cycle. If it is a 5 cycle, it must have an edge, and so on. It has no induced cycle other than triangles. So this says that, I said that induced subgraphs will play a big role. Here is this. Using this in 2000, Herzog, Hebe, Zeng proved a purely algebraic result that if Ig has linear minimal free resolution, then for all s greater than equal to 2, Ig power s also has linear minimal free resolution. Now, from algebraic perspective, this is a stunning result. I mean, forget about general ideals, just go to square free cubic. This just goes out of the window. This is extremely counterintuitive why Ig having linear minimal free resolution should control the higher powers, and not just any higher power, all higher powers. These two together just opens up the huge window of possibility. Now that you have this really concrete thing, one must explore what are the other very concrete things one can study, and possibly build a dictionary between algebra and graph theory. And just a passing remark, this is not related to today's talk that much. I just briefly mentioned Cohen-Macaulayness. One can characterize edge ideals of bipartite graphs, which are Cohen-Macaulay, extremely concretely. So that also falls in this big general picture, and that was also done by Herzog and Hebe. So there were lots of results of the similar flavor that was coming. So Francisco Ha and Van Tool, during their personal communication, observed the following results. Oops, sorry for this typo. There shouldn't be any F. There should be if. If Ig power S has a linear minimal free resolution for some S, then there is no induced 4 cycle in G complement. So this is a weaker, the converse of this result, the Herzog-Gibbs result. Any power has linear minimal free resolution, then there is no induced 4 cycle in the complement. Also, I don't know whom to attribute this result honestly, because this is very easy to prove, like 2-line proof. I read it, I think Francisco Van Til knew this, but I also read it in Nivo-Piva paper. And I think this is given as an exercise in Miller-Sturmfeld's combinatorial commutative algebra book. So I'm not sure who honestly did this first time. If Ig has linear presentation, that is in the resolution, the D1, not the 0th map, the first map is linear if and only if no induced 4 cycle in the G complement. Any questions so far, by the way, about whatever the picture, the general picture we are discussing? Should I move on? Okay. So using, in light of these, Francisco and Van Til asked the following question. Let G be a graph which doesn't have any induced 4 cycle in its complement, then is it true that Ig power S has linear minimal free resolution for all S greater than or equal to 2? We already saw that if any power has linear minimal free resolution, then complement has no induced 4 cycle. Can we at least say that higher powers? Now, okay, one may ask why you take S greater than or equal to 2, but S greater than or equal to 2 is needed because of this example. See, this is a 5 cycle. Complement of a 5 cycle is a 5 cycle. So complement does not have any induced 4 cycle. Okay. Complement doesn't have any induced 4 cycle, but we saw this doesn't have linear resolution. So complement not having just induced 4 cycle is not enough for linear resolution. You need complement doesn't have any induced cycle, period. However, we are coming very close. I mean, G has no linear minimal free resolution. Then it has linear minimal free resolution implies all higher powers have linear minimal free resolution. Any higher power having linear resolution implies no induced cycle in the complement, and linear presentation if and only if no induced 4 cycle. Maybe one can ask this question, that no induced 4 cycle may not imply all powers have linear resolution, but it may imply all higher power, namely 2 onward has linear resolution. So by the way, it is very clear that all powers from 2 onward having linear resolution is actually a weaker condition compared to just the first power having linear resolution. Eran Nivo and Irina Piva, Nivo was a postdoc at Cornell that time with Piva, answered this question that unfortunately this is not the case. The counter example was very large, and this was obtained by triangulation of a sphere. It's something like the graph which gives the counter example, its complement is something like how many? Something like 12 vertices, 120 edges or something like that. It's very large and computation takes lots of time. However, experiments done, also the following theorem was proved by Nivo. If G is a graph which doesn't have any induced 4 cycle in the complement, if G has no induced claw, I'll define claw in a moment, then regularity Ig less than equal to 3 and second power has linear resolution. So regularity of Ig square is 4, means basically second power has linear resolution. This is called claw. So in light of these and lots of experiments done in Cornell server, Nivo and Piva came up with the following question. G be a graph which doesn't have any induced 4 cycle in the complement, if regularity Ig less than equal to 3, then is it true that for all S greater than equal to 2, Ig power S has linear minimal free resolution? So the difference between this question and the previous question was just taking no induced force cycle blanketly. And the counter example actually is the case where regularity of Ig is 4. But what happens to 3? Of course, if regularity is 2, then all higher powers have linear resolution, because that's linear resolution. That implies higher powers have linear resolution. What happens to regularity less than or equal to 3? Is it true that all higher powers have linear resolution? This was the question my advisor gave me as a thesis problem. And the first thing I realized, that most difficult part was to go from Ig to higher powers. The Herzog-Hebbe-Zeng's technique was absolutely not generalizable. It uses the Froberg's characterization that no induced force cycle in the complement really heavily. Nevo's result for squares, that too uses some heavy simplicial complex results, which again was not conducive to go from second power to even third power, forget about higher powers. Also, there are things called LCM lattice and other things. Several people tried them without much success. But this claw, I realized that was the issue. This claw had something to do with the whole thing. And this claw came from, again, triangulation of sphere and analyzing the closed structure. So I generalized the claw I realized that a generalization of claw is needed. This is called cricket, which is a generalization of claw. A graph with induced cricket is called cricket free. So the following result became the first result in this direction. For any cricket free graph G, such that G complement doesn't have any induced force cycle, we have regularity Ig less than or equal to 3. And for all s greater than or equal to 2, Ig power s has linear resolution. If you have a 5 cycle, then one can check that it's cricket free and the complement doesn't have any induced force cycle. One can check that these are all higher powers have linear resolution. By the way, 5 cycle is such a simple graph, and one would imagine that people would know a formal proof that all higher powers have linear resolution. In fact, I couldn't find a single formal proof which says all higher powers have linear resolution. Of course, perhaps one can, using brute force technique, one can prove it for some powers, because after all, resolution is computable. But I didn't find a single formal proof. And as far as I know, it's probably the first formal proof follows from this thing. And this should indicate how difficult proving something concretely can become. Basically, what is the regularity of higher powers of general cycles that remain an open problem until 2016 or so, and that became thesis problem of a friend of mine. And her main result in her thesis was to prove a formula which gives regularity for Ig power s, where Ig is an n cycle in general. In my thesis, I also put the following result, that if for any G, such that G complement doesn't have any induced force cycle, if regularity Ig is R, then for any s greater than or equal to 2, regularity of Ig power s is less than or equal to 2s plus r minus 1. Now remember that this is basically one more than optimum possible bound. The optimum bound, because of Herzog-Hebbe-Zeng's result, says that regularity Ig is 2 implies regularity of Ig power s is 2s. So if I had r minus 2, then this would have been an optimum bound. And unfortunately, I couldn't prove it. And but recently, me and Nevo could prove that for any bipartite graph, at least, that optimum bound holds. And for any graph, we can prove it just for the square. The following question still remains open. And by the way, this is a question many people tried in last 6-7 years, and there have been many papers towards this direction, but it still remains open. And people used techniques developed in my thesis as well as other techniques, but I really love to see a solution of this. And I think solution of this problem needs one more sort of push, and that will open up further direction in edge ideal. So this was the result I was talking about. Selvi Bayersland, this was main result of her thesis. She proved that if G is a cycle, then regularity of Ig power s is 2s plus induced matching number plus minus 1. This brings, so she was studying this time the previous question, as well as of course this conjecture about what happens to the graphs, to the cycles. And she and some other people observed that the matching in a graph, whether matching in a graph is just matching number of a graph is the maximum size of disjoint edges in the graph, and induced matching is just a matching such that the induced subgraph on those edges is just which has no other edge. So myself, Bayersland and Ha proved that if regularity of Ig is equal to R, then for any s greater than or equal to 2, then regularity of Ig power s is 2s plus matching number minus 2. Finally, the following question remains open, that whether it is true that for induced matching now 2s plus induced matching number minus 1 bound works for every graph. So let me just briefly give the sketch of the proof that is used in all these results. It's mostly similar. So one basically builds Ig power s from Ig power s plus 1 using the following short exact sequences. You throw inside Ig power s plus 1 generator of Ig power s at a time to build Ig power s here. Now, if you have a short exact sequence, the regularity of the middle is less than or equal to max of the regularity of the sides. So this, note that in the first line, whatever you get in the side comes in the middle of the second line. Similarly, whatever you get in the right side of the second comes in the middle of the second line, and so on. So regularity of Ig power s mod Ig power s plus 1 is just less than or equal to max of the sides and the last one. And the last one's bound, suppose you know using induction, then to bound the regularity of this s mod Ig power s plus 1, all you need is the sides. And what I could prove, that's all these sides are essentially edge ideals. Hence, and those edge ideals are closely related to the graph. Hence, at least with under some condition like cricket free and so on, you can get a bound for those using Froberg's theorem. So that was the scheme of the proof that I developed in my thesis, and many, at least that still is one of the important way to sort of go about these proofs. So just to mention before I end that if G is bipartite, some nice conditions work. Ali Louis and myself could prove that if Ig power Ig is regularity Ig is 3, then regularity of Ig power s is 2s plus 1. So this actually shows that no induced force cycle in the complement is essential. No induced force cycle in the complement of a bipartite graph means no induced cycle, period. Bipartite graphs cannot have any induced 5 cycle or 6 cycle and so on, because bipartite graphs are x's and y's. The complement will have click on x's, clicks on y's. So if you have a 5 cycle or 6 cycle and so on, it must have at least 3 x's or 3 y's. So there will be an chord. So bipartite graphs, no induced force cycle in the complement implies all its linear resolution, and hence all powers have linear resolution. If you drop that condition, it's not linear resolution, but you have an exact formula. Also for bipartite graphs, there is another nice thing called depth. For if the graph is unmixed, by that I mean essentially that all vertex covers, minimum vertex covers have same size, then one can nicely characterize this so-called depth, which is basically an invariant related to the length of the resolution. One can get pretty nice characterization of that. So I mentioned Cohen-Macaulay and also unmixed. So whether one interesting question is whether one can classify all such things. So Yogesh and myself worked on a random version of this thing, namely what happens that if you take finite simple graphs, but they are actually random graphs. They come from Erdos-Renyi model. Can you give a probabilistic dimension to this whole picture, namely this linear resolution, linear presentation, and all these things, whether you can give a probabilistic angle to it. And actually, some really nice things happen there. And that's what we could prove, that this Nevo-Piva conjecture becomes redundant, and as well as the regularity satisfies some kind of law of large number. And of course, this is just the tip of the iceberg, we hope, and lots of things one can possibly explore in this area, which brings probability, algebra, as well as combinatorics. Thank you. I end here.
Okay, so any questions? Questions or comment, anything?
Yes, I have one. So, before the sketch of the proof, can you go back to the slide?
Yes. Yeah.
Oh, yeah. In the theorem of which you proved with Bayes and Ha, what's the role of the regularity of IG?
That's actually a good point. I doubt. Okay, we don't need it. I mean, that's just a redundant statement. Yeah, thank you.
Yeah, so okay, so induced matching, you mean matching number and the induced matching number there?
Yeah.
Oh, okay. So it's -1 here.
Yeah, yeah.
Yeah, thank you.
And here, do we initially assume that the graph which is given is connected?
No, nowhere.
Okay, so this works for disconnected graphs as well, right?
Yeah, sure.
Okay, thank you.
Yeah,
one
one more
question.
general question. So regularity of, so in place of edge ideal, if you take something called click ideal, or like you must have seen that, where you define x1, x2, x3, or maybe x1, x2, x3, x4 is generator of a generator of the ideal if they form a click in the graph, something like that.
I know only one paper studied the click ideals. It's by, I think, some Iranian person.
Yes.
Yeah, there is one person who studied. I actually don't know much about click ideals. So there are various generalizations of edge ideals, like click ideals, path ideals, and so on. I honestly don't know if nice characterizations too came up there. I mean, I think those are the things I would say. I think better word will be their work under progress. Yeah.
Okay. Yeah, thank you.
One question related to what someone asked about connectedness. Is there anywhere being connected or disconnected shows up algebraically in this edge ideals? Does one have some difference? Can you detect it algebraically?
See, algebraically, this becomes, honestly, algebraically. So if you, for example, have a connected graph, okay. First of all, connected graph, if you're disconnected, the only case where things may get slightly complicated or slightly, let's say, messy, is that if you have isolated vertices. If you have two disjoint components, that's it, then no problem appears. It's just two disjoint, the ideal has two disjoint set of generators, so what? So the isolated vertices, how do you really interpret the edge ideals? Algebraically, it doesn't change much, because you can interpret in two ways. For isolated vertices, you can either put the vertices that essentially, since you're at the end of the day, you, from algebraic point of view, you essentially study the quotient ring. What it does is that you have isolated vertices in the quotient ring. You're basically studying a smaller ring. That's it. You boil down to the smaller ring. And that's same as studying the smaller, if you just don't put the isolated vertices, because anyway, adding some redundant variable in the embedding ring is doesn't change much. From a geometric point of view, as long as you have an embedding, if you redundantly keep embedding into a higher space, it doesn't change much.
Okay. Okay. Thanks.
Anything else? Any other questions or comments?
Hello. Yeah. So, what is the definition of random graphs?
So you will get a fuller treatment tomorrow, I think, in Yogesh's talk. So random graph is, so at least the model we are taking here is you fix a number p between 0 and 1, and so you fix the vertices, n vertices, x1, x2, xn, and each vertex, sorry, each edge, say x1, x1, x2, xi, xj, the probability of xi and xj being there, xi, xj being there is p. And probability of xi, xj and xi prime, xj prime, the xi, these two edges are independent even. Whether this edge stays or not doesn't affect whether the other edge stays or not. So basically, this gives you a model where there are 2 to the power n many possible graphs, or not 2 to the power n. I think n choose too many possible graphs. Sorry if I'm messing up binomial coefficients. And for each graph, the probability is, whether this edge is there. Wherever there is an edge, you take p, and wherever there is no edge, you take 1 minus p. So so there are these many possible graphs. So okay, if there are n many vertex, how many possible finite simple graphs are there? Okay, write down those graphs and assign a probability accordingly. Where if an edge is there, if k edges are there, take p to the power k. If and then n minus, and then for the remaining non-edges, take 1 minus p to the power that power. Sorry, I was being bit hand wavy. I think Yogesh will do a fuller treatment of that tomorrow.
Okay. Okay. Thanks. Yeah.
Any other questions? If not, then I request all of you to just unmute yourself and thanks the speaker by clapping yourself. Okay, so the next talk for this series is tomorrow at the same time, 11 a.m. And the speaker will be Professor Yogeshwaram from ISI Bangalore. And this will be the follow-up talk from today's talk, and he will be speaking on edge ideals of random graphs. So thank you all for coming, and thanks Arindam for such a nice talk. Thank you all.
Just to announce that the video of this talk will be available on YouTube in case you want to go back and see anything, and we'll upload it on web page also.
And thank you very much, the organizers, for inviting me, and thanks for organizing this.
So please, Arindam.
Yeah.
It was good to speak in front of a non-algebraic audience for the first time. It was very exciting.
Yeah, thank you for giving such a wonderful talk. Yeah. Okay, so I'll end the meeting for all, and we'll see tomorrow. Meet tomorrow.